Hello class, I hope you're having a wonderful day. Today I would like to take a look at a problem from Chapter 6, Motion in Two Dimensions. So I'm going to read the problem to you, underline some important information. We're going to list some knowns and unknowns and draw a picture to help us solve the problem. So let's go ahead and get started. A dart player throws a dart horizontally at 12.4 meters per second. The dart hits the board 0.32 meters below the height from which it was thrown. How far away was the player from the board? Okay, so we've underlined some important information. Let's generate a column of knowns and unknowns. So our initial velocity in the x direction, identified by v sub I sub x, is equal to 12.4 meters per second. Now the problem tells us that it's thrown horizontally. So initially, the velocity in the y direction is 0. v sub I sub y, 0 meters per second. So the dart hits the board 0.32 meters below. And so when we talk about displacement, remember displacement is a vector. So when the dart player throws the dart, it falls due to the acceleration due to gravity in the negative y direction. So our displacement is negative. And we're going to identify that by final displacement in the y direction. It is negative 0.32 meters. Now the problem wants us to calculate how far away the dart player was from the dartboard. So we're going to have to calculate the final displacement in the x direction. Okay, so this is our unknown. This is what we need to calculate. Now if I was going to draw a simple picture here, we have the dart, initial velocity in the x direction, and it is 12.4 meters per second. It says it loses some height right here. And we will call this the final displacement in the y direction. And we have indicated that that is a negative 0.32 meters because it falls 0.32 meters. And we need to calculate the final displacement in the x direction. And we're identifying that by d sub f sub x. Now the first thing we need to do is calculate the final velocity in the y direction. And we're going to do that by using the base equation, final velocity squared equals initial velocity squared, plus 2 times the acceleration multiplied by the final displacement. Now, since we're working with motion in two dimensions, we're going to adapt this equation to what we have going on in our situation, and we're going to adapt it to the y direction. So the final velocity in the y direction squared is equal to the initial velocity in the y direction squared, plus 2 multiplied by the acceleration in the y direction, and this is the acceleration due to gravity, identified by lowercase g, multiplied by the final displacement in the y direction. Now, what's easy for us in this problem is this variable here, the initial velocity in the y direction, and that is squared. But at 0, we have already identified that the initial velocity in the y direction is 0, okay? This guy goes to 0, we don't need to mess with it anymore, okay? So 2 times the acceleration due to gravity, that's negative 9.8 meters per second squared. And then we're multiplying by the final displacement in the y direction, negative 0.32 meters. So go ahead and grab your calculator. So 2 times negative 9.8 meters per second squared, that's negative 19.6, times a negative 0.32. this gives me a positive 6.272 meters squared per second squared. Now, on the left-hand side of the equal sign here, we have final velocity in the y direction squared, and we need to get rid of this squared. Let's get rid of this exponent, and we're going to do that by taking the square root. But remember, to keep the equation balanced, what you do to one side, you have to do to the other side. So that means we have to square root the right side of the equal sign. Now, back to the left-hand side of the equal sign. The square root of a squared value, that cancels those out, and we're just left with the variable final velocity in the y direction. So right here, let's take the square root of this value, and we get 2.5. Now remember, not only are we taking the square root of the numerical value, but we're also taking the square root of the unit value. So the square root of meters squared per second squared is just meters per second. Now we need to remember that this is velocity, so it's a vector, and it will show not only magnitude, but it shows direction as well. So we know that the final velocity in the y direction is negative because it's going down. So we need to indicate the downward direction. We could put a negative sign, we could say negative y direction, or we could say down. Any of those will work, but I like to use the negative sign, okay? So the next thing we need is the time that the dart is in the air. And since we know that the initial velocity in the y direction is 0, and we know the final velocity is negative 2.5 meters per second, and we know the acceleration in the y direction is the acceleration due to gravity, we can calculate the time that the dart is in the air. And we're going to use the base equation. Acceleration is equal to the change in velocity divided by the change of time, okay? So this is going to be final velocity minus initial velocity divided by time. Now I want to be a little bit more specific here and adapt this to my situation. The acceleration in the y direction that the dart is experiencing is the acceleration due to gravity, identified by lowercase g. Then we have final velocity in the y direction minus initial velocity in the y direction, and then divided by delta t, okay? So our unknown is on the right-hand side in the denominator. So I'm going to multiply by time interval on both sides of the equal sign, and then divide by the acceleration due to gravity. So what I have is delta t is equal to final velocity in the y direction minus initial velocity in the y direction divided by the acceleration due to gravity. Now right here we know that the initial velocity in the y direction, you've already identified that it is 0 meters per second, so we can get rid of it. It goes to 0. So final velocity in the y direction, you've calculated it here at negative 2.5 meters per second divided by the acceleration due to gravity, negative 9.8 meters per second squared. So my time interval that the dart is in the air is 0.255 seconds. Okay, and so what I really want to do right now is just revisit our units. So in my numerator we have meters per second. In my denominator we have meters per second squared. And let's just kind of think about the old algebra rule. Whenever you divide fractions, it's like multiplying by the inverse of the denominator. So what we have here is meters per second times the inverse of the denominator. We're going to have seconds squared per meter as you can see, the meters cancel out and one of our seconds cancels out. So meters, that's gone. One of our seconds is gone, leaving us with units of seconds. Okay? Now, we know that we can calculate the displacement of an object if we know the average velocity and the time. So that is d equals v bar delta t. Okay? So if we use this right here, this equation, and we adapt it to our situation, what we have is the final displacement in the x direction is equal to our velocity in the x direction multiplied by our time interval, okay? And the problem wants to know how far away. So this is what we need to calculate, the final displacement in the x direction. So my velocity in the x direction was given to us in the problem, 12.4 meters per second. And the dart was in the air for 0.255 seconds. So we can just take the product of these two values. And I get 3.16. So our displacement in the x direction right here is equal to 3.16. Now let's take a look at the units here. I have meters per second for velocity, and I have units of seconds for my time interval. We can write this as seconds over 1. Our seconds cancel, leaving us with units of meters. So the dart player was standing 3.16 meters away from the dartboard. Well, I hope this helps you working through this problem. If you need any help, please send me an email or call me or contact me through your Canvas account. I hope you have a wonderful day.